All right. Good evening, good evening, good evening. We are starting our monthly Astronomy on Tap. How are we doing tonight? You know what? I gotta go. That wasn't good. How are we doing? All right. Thank you. A little better. Yeah, we got a good one tonight. First timers. Anybody first time here tonight? Good. Welcome. Always good to see first timers. And I guess everyone else has been here once or twice, been around the block? No? All right, it's whatever. Yes, I'm Aaron. That's Sam over there, Michael, Brian, and Adam, keeping the show running. Michael, what is Astronomy on Tap?
That's a great question. Astronomy on Tap is a worldwide phenomenon. As you can see on this map, there are locations all across our globe. It started just over 10 years ago in Brooklyn, New York, and our own location is now, I believe, just over 5 years old, almost 6, actually. And yes, we're all over. But our specific one is fun, interesting. I guarantee that you will find interest in our talks tonight because they're that cool. They are interactive because, yes, you will get to ask questions. So if you have any questions, we will have a way for you to ask them via phone number, text. We'll have more information on that. And lastly, we offer a chance to win because we will have trivia at the end. So please stick around if you can. We'll have some great prizes, including some lunar prints. For those of you that were here last time, Robert Reeves had some prints, and he's actually talking about the mission tonight that took those prints. So it's a fabulous prize, and you'll get to learn the in-depth story about them. So that'll be a lot of fun. And as always, please check us out on our socials. We post information about our upcoming events, and this month, is going to be a crazy ramp-up because the eclipse is imminent. So we're all excited about that.
All right, we have two excellent speakers lined up today. Our first is Dr. Xinting Yu. Hold on a moment. I'm not going to read that whole title. It's about Saturn's moon Titan. Then we will have our typical break and Astronomy Club's Astronomy in the News, hosted by Caleb Gamar. And finally, Robert Reeves will be talking about Lunar Orbiter and the Moon, which is the topic of the trivia prizes. We wanted to give you a fantastic explanation on that. So, I believe that's all the announcements I have.
Advance the slide. Click down. All right. I will now introduce our first speaker, Dr. Xinting Yu. Dr. Yu is a current assistant professor at the University of Texas at San Antonio, our very own UTSA. Previously a 51 Pegasi B postdoc fellow at UC Santa Cruz. She received her PhD in planetary science from Johns Hopkins University and a Bachelor in Science in Space Physics with honors from the University of Science and Technology of China. 51 Pegasi B, just quickly, that's an exoplanet, right? The first exoplanet, so that's why the fellowship is so fancy. And without further ado, we will begin our talk, but before I forget, we always forget, those of you who've been here before, you know what I'm about to introduce, but for those of you that are new, we have a drinking word. Now, first of all, be responsible. You all have to drive, so use water if you have to, but Xinting will say a certain word, and we will all toast and go, woo! So let's get that word. What is that word?
Magic.
So magic. There we go. We're ready to go. Without further ado, Xinting Yu.
First drink, you guys. Magic. How is everybody doing tonight? How are you guys? Good? Yes? Okay, magic will show up later, but many times. So you guys will keep drinking. Yeah, my drink. All right. How many of you here have never heard of Titan? Raise your hand. Oh. Surprise, surprise. Okay. But today I'm going to be talking to you guys about my favorite moon in the solar system, Titan. And we're going to do a flight over Titan's mysterious hydrocarbon lakes. Okay? All right. Cool. Okay, in the next couple of slides, I'm going to try to persuade you. Actually, Titan might be one of the most Earth-like planetary body in the solar system, okay? So those of you who don't know Titan super well, it's the largest moon of Saturn, okay? But even though it's like the largest moon of Saturn, it doesn't mean like it's super big. It is bigger than the moon, our own moon, but it's like much smaller. It's about the third the size of Earth, right? So that means the gravity on Titan is much smaller, okay? But here comes the similarity. So if you look at Titan's atmosphere, okay, Titan actually has a very thick nitrogen atmosphere. And do you guys know what is Earth's atmosphere made of? I ask this to my students all the time, and I'll get weird answers. Anybody knows? Nitrogen, thank you. Some people would tell me we have a CO2 atmosphere, or like an ozone atmosphere sometimes. But anyways, Earth has a nitrogen atmosphere, right? And Titan does that too. And the surface pressure on Titan is actually more than even Earth. It's about 1.5 times Earth's surface pressure, okay? But you're wondering, okay, like Earth doesn't look like a giant yellow ball, right? Like it has a nitrogen atmosphere, but it doesn't look like this. And the reason we're seeing Titan looking like this in the visible, like a giant yellow ball, is because there are these thick hazes, haze particles that are floating around in the atmosphere that are blocking the visible light from seeing what's happening on the surface, okay? So what is happening here? So on Titan, there's actually one ingredient that Earth doesn't have, which is methane, okay? So there's a bunch of methane in Titan's atmosphere, about 1 to 5%, depending on where you look at. And then because Titan's atmosphere is exposed in this energetic environment with UV photons coming from the sun and the energetic particles coming from Saturn's magnetosphere, you can initiate this really fabulous chemistry in Titan's atmosphere, making lots of interesting molecules. So here are just some examples showing you these are just some of the molecules we have detected in Titan's atmosphere already. So who loves organic chemistry in high school, say? Raise your hand. Like nobody? But anyways, I love organic chemistry. But you form all these fabulous simple organic molecules, and these molecules could further polymerize and coagulate to form more complex haze particles that are about micron size. And these are the particles that float around in Titan's atmosphere, okay? You're like, Earth is not covered in these yellow, like, haze particles. But I'm going to make an argument that, okay, actually, in a long, long history, far away from now, Earth actually used to have no life, okay? And we believe from the geological record and all of the evidence we have from the early climate studies, Earth's atmosphere actually happens to be pretty reducing in the past, which means instead of having a bunch of oxygen, Earth's atmosphere actually used to have a ton of methane, okay? And similar to Titan, Earth's atmosphere is actually exposed in this kind of energetic environment as well, with lots of UV photons coming from the sun, and Earth is even closer to the sun, right? And the same process can happen in this early Earth atmosphere, making these organic molecules. And the interesting thing is, there are lots of people who study the origin of life, right? They're trying to figure out why would Earth even have life. And even though there are lots of disagreements upon like how Earth's life originated, everybody at least agree this photochemically formed organic molecules may at least serve as an initial like soup or the organic matter for life to start brew upon. So it's like, the base for you to brew your beer, to brew your life, okay? So that's why like Titan is interesting. So now if we move on to what's happening on Titan's surface. So apparently Titan's the haze layers are so thick that you can only use particular wavelengths to look at what's happening on Titan's surface. And in this case, we can actually use radio wavelengths, which is by using radar instrument to look at what's happening on Titan, okay? So here I'm actually showing you two images. One is an image for a lake on Earth, and then another image is for a lake on Titan. And they're both taken using radar, okay? But one is orbiting Earth, one is orbiting Titan. I'm gonna make you guys make a guess. Which one is Earth and which one is Titan? Think about it. Okay, I'm gonna think about it. Okay, who thinks the left image is Titan? Raise your hand. Okay, all right. Okay, who thinks the right image is Titan? Okay, so we get equal amounts, right? I can't really tell, you guys. It's really hard for me to tell. Sometimes you can have these Earth images. They're like rows connected to it, but not this one. But this is what it is. Why you guys like kindergarten kids? Oh my God. Okay. Anyways, don't you guys? Okay. Don't you guys find it weird? So here I'm summarizing some of the environmental conditions we found on these two planets. Okay. Do you guys find this weird? Okay. On Earth, what are the lakes made of? You guys? Water. Thank you. Okay. Okay. What are the lakes made of on Titan? It's freezing cold there, so it's 94 Kelvin. Do you guys think lakes are made of water? No, okay, but this temperature is actually a magic temperature to methane. Drink. Because methane's triple point is about 90 Kelvin, okay? And on Earth, the triple point of water is actually very close to the surface temperature of Earth. And on Titan, similar things happen for methane. So methane can freely transform between a liquid and a gas on Titan, okay? Making these fabulous features that looks like lakes, but made of liquid methane. And what happens to all the water on Titan? They're all frozen up. So all these lands you're seeing on Titan, they're frozen up water ice rocks, okay? All right, so these are the lakes, and they look pretty similar, right? Now I'm going to tell you something weird about Titan, all right? So even though the lakes looks really similar morphologically to the lakes on Earth, they're just small images. So this is small images taken by the Cassini-Huygens spacecraft. So this is a spacecraft that we sent to Titan from 2004 to 2017. And this is an image taken by the Huygens probe. So we sent a probe actually on Titan. So it landed in the equatorial regions of Titan, and during the descent, you can see this nice river channels flowing. So don't these remind you of the river channels on Earth, right? So this is fabulous, but again, made of all liquid methane, okay? And lakes are everywhere on Titan, and on Titan, most of the lakes are happening in the polar regions. In the equator, it's pretty dry. You can ask me about Titan's climate. I can talk for another hour probably, but I'm gonna stop right here. And talking about the differences. Okay, so you all have seen like waves. Who has done surfing in the past? Some of you, but you experienced waves, right? Okay, wave is a common thing for like lakes or seas on Earth, right? But apparently Titan is really, really strange because on Titan, the lakes are super, super smooth. So we're talking about these waves that are measured to be less than 3 millimeters. Okay, 3 millimeters, I don't know, like it's just nothing, okay? And we measured over the years, and it's like we didn't see any waves. So it's quietly and ghostly smooth, and we have no idea why. And one of the hypotheses people had is, okay, if you can have a floating layer of maybe organic materials that are coming from the atmosphere, they just float on the ocean, maybe those can serve as a material to dampen the waves. Just like if you have an oil spill on the ocean, you can actually dampen the waves on the ocean, okay? And I'm gonna show you a video. Let's see if it works. If this can play, let's give it a try. Oh, the video doesn't play, but if you look up like oil or dampening waves, so this video is basically showing you a guy. This is like a pond with some like little waves, you can see it, okay? And then he just literally have like a spoonful of sunflower oil dropped into the water, and then all the waves are gone. So this oil kind of serves like a dirty like carpet. It just like drags around because of like how oil like moves. It's like moves less compared to water. It's like just dampens the wave completely. And people even do that when people sail on the ocean. The sailors sometimes they bring oil with them to kind of smoothen out the wave, near the ship they're on actually. So this is like a thing that happens. But this is one weird thing about Titan. Second weird thing. Oh, okay. Here they go. We see these features called magic islands. Okay. So just imagining, well, not imagining. So here I'm showing you like a pretty big lake. So this is the second biggest lake on Titan. And if you stare at this green kind of circled area, this is like an island protruding to the lakes, okay? You just stare at it, and you take another picture, and you're like, okay, what the heck? Like something suddenly showed up in the image, okay? And then apparently it showed up, and then it disappeared again, and then it showed up again, and it disappeared again. And we kind of have no idea what these magic islands are. I'm gonna give you guys a second to think about it, okay? But we have been studying these magic islands for years. Okay, I shouldn't be saying that too much. And I would say these are the hypotheses that are left to explain these weird phenomena that we see on Titan so far, okay? And I don't know if you guys notice any like commonalities in these hypotheses, but the first one, but what we actually interested in studying is like how can you have like floating stuff explaining the smoothness of the lakes? Say if you have a thin smear of organics floating on the lakes, you can dampen the waves, so maybe that's why the lakes are so smooth. And if you have a big chunk of stuff floating on the lake surface for some time, that can maybe explain these magic islands. Okay. I'm having a hard time drinking this, but all right. So this is our paper that's actually published in January this year. I don't know, like people loved this paper somehow, and it got on CNN news apparently, and my parents are really happy. That's all I know. But we're talking about basically floating solids can become the material to make magic islands. I'm making you guys drinking a lot, sorry. Okay. All right. So to really understand this, we want to understand, okay, how do these atmospheric formed, photochemically formed organic material interact with the lakes on Titan, right? And we really want to understand their fate. For example, do these materials dissolve completely and become just part of the lake liquid? Or maybe they would float to make the stuff we want, to dampen the lake waves and also make magic islands. Or maybe they would sink and become lakebed sediments. Oh my God, I'm really making myself drinking too much. I choose a wrong drinking word, apparently. All right, so we had a paper published a couple of years earlier studying how the complex organics interact with the lakes, and this new paper we were doing was actually studying how these simple organics were interacting with the lake liquids. But anyways, we use a database that's developed by my own group with generations of undergraduate students and also some of our laboratory measurements. At the end of this talk, I'm going to show you some of some nice images of my lab. But basically, what we found is none of the stuff would completely dissolve in Titan's lakes. So that means any incoming material from the atmosphere would still be able to remain as solid when they interact with the lake liquids on Titan, okay? So that leaves us to float or sink. And this is really not a hard physics question, right? If you think of a particle falling onto a surface of a lake, there are only pretty much two forces that governs whether it floats or sink, right? One is the capillary force. So think of there's some insects, they can walk on the ocean or on these lake surfaces. And this is caused by the surface tension effect. And this capillary force can always give you this extra leg to make things float. And then we also have the net buoyancy force that's basically comparing the density of the material to the lake liquid. And basically, if your material is less dense compared to lake liquid, you're gonna float. But if your material is actually denser than the lake liquid, you're gonna sink. So the first thing, the easiest way to make things float is, well, if your material, the density is less than the lake liquid, you can just naturally make things float. So we first look at how the density of these organics that are falling from the atmosphere compared to the lake liquids, and we found everything is denser than these liquid methane lakes, okay? And then we also evaluated, okay, how much porosity assuming these organics coming from the atmosphere, they're usually not just like a solid piece of material, but they have pores in their structures. So how much pore space is necessary to make them float? And is this reasonable? And based on our calculation, it is indeed reasonable for some of these ices to float, by having enough porosity in their structure. And we also evaluated, say if these particles do not have enough porosity, they're denser, right? We know that. How much capillary force is kind of available for them to make them float? And we did this calculation also, and we showed that apparently there's only one ice can float on Titan's lakes, and it's called hydrogen cyanide. Anybody heard of hydrogen cyanide? Yes? Okay, don't drink it. So it's pretty unhealthy for you, I would say. All right, so this is the only ice that can be supported with capillary force to float, okay? So what we found is basically, if you want to float something on Titan's lake, you either want a fluffy particle or hydrogen cyanide ice on acid-rich lakes, and everything else would sink, okay? But in order to make the magic island happen, oh my God, I'm making my life so difficult. Oh, sorry. You not only have to float, but you have to float for the right amount of time. Which means you can't float for a second, right? Because if you float for a second, we wouldn't be able to see it for some time. You can't float there forever. Then it will become a permanent feature. So we think how long these magic island features show is between a couple hours to a few weeks. And if we examine whether capillary force-induced flotation can last this long, apparently it lasts too long, because once you sustain flotation with capillary force, you're never going to sink. It's going to happen really forever. So we don't think this is going to do to explain the magic islands. But if you have these porosity-induced flotation, though, it really depends on how long does it take for all this liquid to go inside the pores to the point that the density of the material equals to lake liquid. And we did this calculation. Apparently, it's a very size-dependent process. And if you have a very small particle, it's going to take barely like a second for these particles, this liquid, to flushing into the pores and make the particle immediately denser than the lake liquid. But if you hit the right amount of size, which is about, according to our calculation, about 5 to 6 millimeters, you can actually hit a regime that's just right, which means you can float for days and months and then sink. So it's going to take that amount of time for the liquid pores to be filled. And that's actually quite similar to this quite common rock we see on Earth, pumice. Anybody heard of pumice? Any ladies will use it for your manicures, stuff like that? Yes? Okay. So pumice is a very porous rock. I actually have one today. So, oh my God, where's my pumice? Somebody steal my pumice? So I do have a pumice today. It's like very light. Even if I'm holding like a piece like this big, I will be able to lift it, no problem. Okay, I'm not extra strong, by the way. So it's a very, very porous rock. So this is kind of the analogy we're making. And the idea of having pumice-like rocks really, oh, I'm going the wrong direction. Here we go. Really helps understand, what kind of processes contribute to the making of the magic island phenomena on Titan. So these are some of the processes we summarized that could make the magic island phenomena happen, right? Apparently, some of the processes will make particles that are too small. So if you're just raining down stuff or like having snowfalls coming from the atmosphere, you're not going to make particles big enough to float long enough. And this kind of makes sense, right? Because if you have snowfalls, it could happen anywhere. Why would it happen next to like another island, right? So we think that's why some of the other processes are more likely to make large enough particles, such as runoff from nearby islands, or maybe transient undersea cryovolcanoes. And I believe that's towards the end. And now I'm going to give you a brief tour of my lab. So my lab, actually, we measure a range of material properties. So I didn't talk about any of the calculations we did, but they're only possible because with the material property we measured in the lab for lots of cryogenic hydrocarbon ices and organic material we simulate on Titan. And we do lots of our measurements under inert oxygen water vapor-free environments. And this is a logo of our lab, Planetary Material Calculation Facility, PM chef, because we only do experiments in the afternoon. So it's PM, not AM chef. And this is just showing you like an image, a corner of our lab. So this is showing you one of our instruments measuring the mechanical property of samples in a dry nitrogen glow box. So if you're near UTSA, maybe you can drop by, and maybe I'll give you a tour of my lab. And I'm gonna leave you the final slide for any questions. So we do believe floating solids, which according to the press, they're like Swiss cheese. You guys are all familiar with Swiss cheese, not pumice apparently, could make these magic island phenomena happen on Titan. And I'm gonna leave my final slides for any questions you guys might have. And thank you all.
All right, thank you, Xinting. Yes, so the number is at the top of the screen here if you'd like to text your questions in. The first question is, are the magic islands dependent on how far from the coast they are? Some structure in the radar images stays the same over the time.
Can you repeat the question? I was drinking. I was trying to compensate for the drinks. I didn't drink when I say the word.
So it appears that the Magic Islands were close to the coast. I think that's what the question is getting at. Yeah. And then is there a dependency factor on that, or is it just chance?
That's a great question. So in this case, we do think it's a dependency because, if it's just random process from the atmosphere, it could show up anywhere on the lakes. But since it's so close to another island, we do believe runoff from another island is more possible. And it also makes the right size of sediment to make it float for that amount of time. So yes, that's a true statement for this kind of observation.
Thank you.
And great question.
The next question is, how do we know that these magic islands are not due to the liquid levels rising and falling? So like revealing undersea
That's a great question because apparently I had, 4 remaining hypotheses for magic islands. One of them is actually bubbles. So we don't know yet, but we're actually planning on doing some more observations, well, digging into the archive data of Cassini. So the idea is if you look at the lake liquids, and then you use some infrared compositional imaging, and if the composition of the magic island drink changes, then that tells you it's actually solid material rather than fake or like bubbles, which should be the same composition as the lake liquids. But we're actually looking forward to do more observational campaign digging into like archival data of Cassini Huygens to see if we can like really determining which process is happening, making it happen. Another question?
Does Saturn cause tides on Titan?
What's the question?
Does Saturn cause tides on Titan?
Yes. And that's something actually was ruled out initially. So the time we see these phenomena, like the tide is not that different during all these times. So we do not think tide is causing, like the shoreline increase and decrease. And also like to make these happen, it has to be like a 60-meter decrease in the shoreline height, which we think is pretty hard to achieve, I would say. So we don't think that's happening to explain the magic islands.
Does atmospheric pressure vary on Titan? Could variations in this pressure cause masses to sink or float if buoyancy is near neutral?
That's another good question. Over the long-term geologic timescale, we do think it might be able to vary, but over the time scale of the magic island phenomena, the pressure is quite stable. Titan's atmosphere is actually quite stable. The temperature is maybe pole to pole is only like 3 kelvins different. Pressure is about 1.5 bar. It's like quite stable. It's like a pretty stagnant atmosphere. It's unlike Earth. So it has 1 Hadley cell from pole to pole. Okay, I should stop talking about Titan's climate because I can go for hours.
Is the structure of the islands consistent when they reappear, or are they a different shape each time?
It's pretty hard to see. So even though these are the best images we have for Titan, they're about each pixel. We're talking about like 100 or 200 meters. So it's really hard to see like the exact shape of the island. And we've seen it maybe twice on like three times on like 3 spots. So it's kind of still hard to make any statistical conclusion about their shape. But so far they do look pretty random. I would say they don't have a particular shape.
Very good. Let's see if there's any more questions. Send them in. Those were some great questions, by the way.
You guys asked some
Very
hard questions.
good
Oh my
questions.
God.
Okay, here's a good one. I like these. How did you start your research on Titan? What got you invested in it?
You guys, I love organic chemistry since I was a high school student. That's like my favorite thing. So Titan is that's where you can do all your organic chemistry work. So I don't know if any of you are into organic chemistry. Maybe you can join my group.
Well, I think that's a good one to wrap up on. Let's thank our speaker once again.
Thank you all.
And so we are going to proceed to our 10-minute break right on time. So we'll be back around 7:40-ish. Please feel free to continue to order stuff from your wait staff here in the room. Don't go crowd the bar. And we still have our merchandise in front. It's very limited space-wise, but we have stuff. So yeah, we'll see you in 10 minutes. And sign up for our email list if you haven't already.
All right, everybody, we're going to move on to our next segment. We got to hear about some astronomy in the news with our resident astronomy anchor, Caleb Gamar. Take it away.
Thank you. Well, good evening, everyone, and this is Astronomy in the News. So let's go ahead and see what's up in the sky, first and foremost, for the month of March. So we are heading into spring. March 21st, roughly, will mark the beginning of spring. So we are now in a time period where if you go outside, take a look up in the sky, you will see a sky that is transitioning from the wintertime to the springtime sky. So this is the way the sky will look around 10 o'clock p.m. after this weekend. Daylight savings time starts this weekend, folks. Remember that, all right? Yeah. Spring forward! Spring those clocks forward, yes. So these times all start becoming a little bit later that I post up here. So around 10 o'clock p.m. throughout much of the month, go outside. This is about what you will see. The great constellation of winter, Orion the Hunter, is finding its way over toward the western horizon. And the great constellation of spring, Leo the Lion, is heading up in the eastern side of the sky. Now, the planet Jupiter is still visible through much of the month, starting to set over there on the western horizon. So do get a good look at it during the next month or so, because it will get lower in the sky and a lot more difficult to see, especially if you're using a telescope. If you are using a telescope, that very nice crisp view of Jupiter that we have been getting for a while now will start to get kind of muddy as it gets lower on the horizon. So definitely take a look at Jupiter now while you still can. Now there is a really nice binocular sky sight, almost center of the sky. There's this kind of faint upside-down Y-shaped constellation. That is the constellation of Cancer, the crab. Pretty faint constellation. Find a very dark sky in order to look for this. Easiest way to find it is to look for the brighter constellation of Gemini and Leo the Lion. And in between those two you will find Cancer the crab. And if you look at the crux of that upside-down Y shape, you will see with a pair of binoculars a nice, beautiful, glittery field of stars. And that is a beehive cluster. It is a very young, fairly recently formed group of stars in the history of our galaxy. It's about 550 to 600 light years away, so you're looking at it as it appeared about 600 years ago. Really beautiful object, and do not forget to scan the rest of the Milky Way area for more of these nice open star clusters and a few nice gaseous diffuse nebula. As we head on into spring, that Milky Way will start to get lower and lower in the horizon. By the time we are in mid-spring, it'll be very low in the horizon, and you will not have as many of the nice star clusters and things like that to look at until, of course, we get into the summer. So do bear that in mind. So for first news story, it worked. Somewhat. So actually, I do have to give Intuitive Machines a hand. They actually did at least get this lander functioning to the point of starting to land on the surface. It touched down. Unfortunately, it just couldn't stand up straight. It had to tip over on its side. But nonetheless, they were able to get some useful data out of it. So the Intuitive Machines Odysseus lander launched late last month, touched down on the surface on February 22nd, lasts until February 29th. I actually have a friend who's part of an organization called International Lunar Observatory Association, and they had a payload on this lander. I'm wondering how well that actually worked out for them. I'll have to ask him the next time I talk to him. But nonetheless, though, it is a rough start, but it's a start. It's the beginning of some really great lunar exploration to follow. Just a couple of days ago, a new crew launched to the International Space Station. Crew 8 launched late Sunday night. They docked with the space station late Monday or early Tuesday. That is the crew right there, and they will spend 6 months on the space station. That includes 3 American astronauts, Michael Barat, Matthew Dominic, and Jeanette Epps, and a Russian cosmonaut, Alexander Grabenkin. They are joining a series of astronauts and cosmonauts that are already on the space station. And then just as this is going on, NASA recently announced that their most recent intake of astronauts graduated from training. So now they are official astronauts, part of the Corps. Of course, most of them have not flown, and in fact, none of them have flown in space yet. So this group, look for their faces over the next few years. Those are the folks that will be heading up into space in many of the upcoming space missions. And applications for the next astronaut class are now open. So if anyone feels as if they fit the bill, put in your application. All right. So here's another really cool story. ALMA, the Atacama Large Millimeter Array, actually revealed the presence of water vapor around a circumstellar disk, a protoplanetary disk around a distant star. So the distant star is in this gas cloud right here. The star is called H. Altauri. It's about 450 light years away, so that computes to something in the neighborhood of, let me think here, I think 2,700 trillion miles away, very, very far away. How many of you are planning on making that trip any day soon? Few of you? All right, sign up for the astronaut corps and they're coming up here. Maybe you'll make that trip. All right, so anyway, nonetheless, though, really fascinating discovery and fascinating imagery. So the blue highlighted area, that is the radio emission observed as characteristic of water as seen around this circumstellar disk. This image here is an actual radio image of that star and circumstellar disk, that protoplanetary disk. And then finally, the James Webb Space Telescope actually revealed some very interesting information about a really ancient galaxy. This galaxy probably formed, or at least we're looking at it as it formed about 430 million years after the beginning of the universe. All right, very, very ancient view. And this galaxy, surprisingly enough, GN-Z11, was unexpectedly bright. It's a fairly bright object. Now what this means, they found by doing further observations, is that this probably has a very active supermassive black hole at the center. And revolving around this central black hole are a series of helium gas clouds, and you can see the emission from the helium in the infrared spectra from Webb right there. And this is a very interesting discovery because it actually gives some great insight into the formation of stars in these early galaxies, possibly even the genesis of what we call the population 3 stars, the very first generation of stars. So really fascinating science being accomplished there. Finally, what to watch out for in the coming months. So yeah, the solar eclipse, the solar eclipse, the solar eclipse, the solar eclipse. Do not forget the solar eclipse. The total solar eclipse coming up on April 8th. Do not miss it. That is a Monday. And make sure you are in the right place to see it. So bear in mind, if you are on the southeastern side of town, you will not be in a great area. You will not be in the path of totality. You will still see something awesome. You'll put on those eclipse glasses. You'll see the moon moving in front of the sun, but you will not have that moment where the moon blocks the sun entirely and you can see the entire outer atmosphere, the corona of the sun in that view. You have to be in the path of totality in order to see that, which crosses part of the northwestern side of town, and certainly hits many of these towns that are out in the hill country that way. So again, please be in the right place in order to see it. There will be a star observing event at the UTSA campus on Friday night, Celestial Lights. It starts out with a lecture. I think it's at 7 o'clock. If it's not 7 o'clock, it's 7:30. It starts out with a lecture that evening about some subject in astronomy. This one will actually be part 2 of a couple of lectures about how we measure things in space. And then following that lecture, weather permitting, there will be star observing using the telescopes at the Curtis Vaughan Jr. Observatory there at the university. So please join us for that event. If you go out to South Llano River State Park on March 16th, that's a Saturday coming up, a number of us are associated with the UTSA Observatory will be out there observing that weekend. Unofficially, March 9th, I'll be out there and a few of my observing friends as well. I'm going to be trying to do the Messier Marathon, which is hitting, yes, 110 of the Messier deep sky objects in one evening, going from sunset to sunrise. I got 108 out of 110 last year, so we'll see if I can get the other 2 this year. Upcoming public talk by John Mather. The week leading up to the solar eclipse. During that week, John Mather, Nobel Prize winner, won a Nobel Prize for his work on the COBE mission, and also the former chief scientist for the JWST mission. He will be speaking at a couple of lectures on campus. The main public one, if I remember right, will be Thursday evening that week. Please go to the UTSA Physics and Astronomy website and find more information about that. And that is Astronomy in the News. Thank you, everyone.
For reference, that John Mather talk is the day after Astronomy on Tap. Yes, okay. All right. Thank you, Caleb. Our next speaker is Robert Reeves, and Robert sent me a 600-word biography, but I will not read all 600 words. So to summarize, Robert began photographically exploring the moon while in high school, and his lunar photography entry in the Alamo Regional Science Fair won him a trip to the Johnson Space Center during the groundbreaking 8-day flight of Gemini 5 in the summer of 1965. Later in life, Robert has collected many telescopes for various purposes, and he told me that you should ask him about them. Robert has published numerous books on science, nonfiction, and astrophotography, and his latest book, we had some flyers, Exploring the Moon with Robert Reeves, was released in August of last year. I encourage you to check it out. And an interesting fact, one asteroid is named after Robert Reeves. Asteroid 26591 is named in his honor, and asteroid 26592 is named after his wife. And so Robert and Mary Reeves are the only husband and wife team to have sequentially numbered asteroids. Yeah. Very interesting stuff. Robert, what is your drinking word?
Orbiter.
Orbiter. All right. Thank you, Robert.
All right, we got the slide up. Okay, this may be the first time that I know of that the topic at an Astronomy on Tap was driven by the door prize. Now, as you know from last month, if you were here, I inherited 3,000 of the original lunar orbiter photographs that were used at what was then the Manned Spacecraft Center in Houston, now the Johnson Spacecraft Center, for the planning of the Apollo missions. 900 and some odd of them are unique. Over 2,000 of them are duplicates, so I'm making sure they get spread around a little bit. And as part of that, for the next year, we will be giving them away as the top door prize here. There will be 4 of them for a table of 4. Now, the whole theme of our talk tonight is how did NASA do such fantastic photography of the moon with the technology they had back then? You can lay this out on a light table, look at it with a magnifying glass, and see boulders on the surface of the moon. And this was taken with photographic film that was not returned to the Earth. So the technology behind that is rather remarkable. And just the sea change of understanding of the moon because of Lunar Orbiter was amazing. I should start my slides or I'll talk ahead of myself. But when you get the door prize, make sure that you also get the little piece of paper that says what it is. Ah, okay. There we go. Well, I've been in love with the moon my entire life, and my earliest memories of the moon were looking at sunrise or moonrise through my bedroom window when I was a child. And I went through the entire space age, from before NASA to now, and the space age explorations have not stripped the wonder that I felt about the moon when I was a child. Now, there's an actual name for people like me, and before you say it, it's not lunatic. Okay. There it goes. The name is selenophile, a person who loves the moon. Well, I have been in love with the moon since I was in grade school when the NASA and the Army and the Air Force started sending the original Pioneer probes up toward the moon. Of course, none of them made it to the moon. I was in high school when the Ranger program finally made it to the moon, sent back Ranger 7, 8, and 9 close-up images of the moon. But I was an adult, definitely in the thick of things in the Vietnam War when Lunar Orbiter flew. Lunar Orbiter has been close to my heart my entire life because of its redefinition of the moon. So how did it do it? Well, the moon is my playground, so I'm inviting you to come out and play with me tonight and learn a little bit about this. The Lunar Orbiter spacecraft, built by Boeing, back when Boeing can actually build things that don't fall apart. And Eastman Kodak. The Kodak's bid to build the Lunar Orbiter photographic system was actually the highest of all of the bids, but the dry chemical process for developing the film on board to scan it and send the images back to Earth is what won them the bid. All other contractors were using a liquid developer, which in the weightlessness of space kind of gets messy. Spacecraft weighed 850 pounds, stood about 5.5 feet high, spread out 12 feet across its solar panels. The 4 tanks up on top held 262 pounds of fuel, which gave the spacecraft a delta V capacity of a little over 2 kilometers per second to mid-course correct on the way to the moon, slow down to enter lunar orbit, trim its orbit to the photography orbit, and then at the end of the mission, deliberately crash the spacecraft on the far side of the moon. Now, the photographic system weighed 68 kilograms. There were also micrometeorite detectors and radiation detectors on board to characterize the lunar environment prior to Apollo flying to the moon. Now, the photographic system is in that red-colored tub. The rocket on top actually adapted from the Apollo lunar module attitude control system. It's an attitude control thruster off of a limb. The entire photographic system was adapted directly from the Air Force Samos reconnaissance spy satellite. They couldn't talk about it at the time. As far as the world was concerned, Kodak invented this system specifically for Lunar Orbiter. But in reality, it had been flying since 1960. 1960, 61, the Air Force was flying the Samos photographic reconnaissance satellites and using this system to develop film in space, scan the images, and beam them down to Earth. It worked terribly as a spy satellite because it was too slow, but it worked great as a lunar probe. Yeah, the photo system, like I said, in this aluminum tub, peered out through both a wide angle and a narrow angle lens. The spacecraft was just elegant as far as I'm concerned. It's my favorite space probe. There's such a simplicity and elegance of form to it. It just grabs my heart. Now, the photographic system, these gentlemen lovingly gazing at it, like I said, it was developed for the Air Force spy satellite. And there's a little bit of a mystery here. We'll go along here and we'll see something different. Here we've got them looking at it. It's got the film supply and the drum off to the left, the large lens on the left, the smaller lens on the right. And here we see the same thing, this publicity photo from Kodak. And the same thing again in this picture I found on internet. And then we have this picture. The lenses are reversed. The entire photographic system has been turned upside down in the tub. Now, whether or not this is the Samos configuration for the Air Force, I don't know. I haven't been able to find any answers about this. But it's obviously the same system, but turned upside down. But by the time it was in the lunar orbiter, the big lens was on the left. As we see here, the big lens is always on the high gain antenna side. So if you know why there are two versions with one inverted, let me know, please. So, the photographic system on it. How did Kodak get such extraordinary resolution on film and get those images back to Earth by beaming it over a radio signal? Well, the spacecraft carried 79 meters of 70 millimeter SO 243 high definition aerial film. There's special radiation resistant film on an S-star base, so it was thinner and it could carry more film. The developing process mashed the film up face to face with SO110 BIMAT film developer. It essentially looked like another piece of film. And when they meshed together, it would develop the film. Now, they didn't need to worry about archival quality, because once the image was scanned within a matter of hours, that was it. It was on the take-up reel and never see it again. And then it's going to get crashed into the moon anyway. So it was one shot, one scan, that's it. And occasionally you'll see a lunar orbiter picture where everything looks beautiful on it, and then suddenly the image will fade out to white for a couple of stripes and then come back. Well, that's just one that's lost, because the rain in Spain stays mainly on the plain, and sure enough, a thunderstorm over the Madrid station blocked the signal. So we lost that. There's no going back. Anyway, continuing on with this thing, you would think that for a project like this, they would get some really special lenses for it, some high-dollar, custom-made things. No, Lunar Orbiter carried commercial lenses, a commercially available 80 millimeter f2.8 Schneider Kreuznach lens made in Germany. Now, if anybody back in the old film photography days, these are familiar names. These are commercially off-the-shelf available photographic lenses. The same with the narrow-angle lens, the commercially available 610 millimeter f5.6 lens made by Pacific Optical. Pacific Optical is no longer in business, so I'm not able to track down more specific details about that. Shutter speeds, fairly slow, 25th, 50th, 10th of a 100th of a second, depending upon lighting conditions. And there is a motion compensator aboard that sensed the drift of the moon below and would physically move the film platen to cancel out the movement. So we'd have very sharp pictures. As I said, this whole system adapted directly from the Samos spy satellite, although at the time, as far as the world was concerned, it was built specifically for Lunar Orbiter. Now, the film readout on this thing is the key to how they got such extreme resolution transmitting these images to Earth. CBS Laboratories, the same television network that brought you Walter Cronkite, developed the film scanning system for this. A flying spot, 5.6 microns, did 286 scans per millimeter. So basically, the scan was a higher resolution than the film grain. And it broadcast this back to Earth on a analog signal, where the wavelength or the pitch of the analog signal was the various brightnesses. It took 48 minutes to scan each full frame, which is why this system didn't work out too good as a spy, but it worked out real good as a research instrument. Now, the film scanner would scan the system, transmit the image to Earth on a 10-watt analog signal at 2295 megacycles, and would be received on Earth, recorded on tape, played back from that tape through a kinescope, which would then be photographed on 35 millimeter film. And then these 35 millimeter film strips would be manually, physically assembled, and that's why you see the little wild black lines in between film strips on a lunar orbiter photograph. And then, caught me on by surprise there. And then this assembly was rephotographed as a master negative, which then made these prints that we have nowadays. So, getting to the moon. Atlas Agena rocket. Atlas had a terrible track record early on in the space program, but by the time the Mercury program put up 4 guys without any major mishap, and Ranger got to the moon, the Atlas Agena was working pretty good. So it made an impressive looking vehicle. Still, I mean, it's small by today's rockets, but it's still a pretty and elegant machine. Up it went 5 times, flawlessly got lunar orbiter 1 through 5 into lunar orbit with no difficulty. Now, when you launch toward the moon, strange things happen. We're used to seeing these plots on maps where we launch the guys into orbit and we see the orbit as this kind of sine wave thing as it's looping up and below the horizon, or below the equator, and around the world it goes. But when you launch for the moon, we get parking orbit down around Africa, light up the Agena again, propel to the moon, and strange things start to happening. Now the spacecraft is rising above the Earth, is escaping the Earth, flying up to the moon, and as it's rising, the Earth is rotating underneath it, and the ground track appears to reverse. So initially we launch to the east, and then it loops back and starts heading west again. This is what you want to see if you're going to the moon. Ground stations, plenty of them around the world. Goldstone, very famous one. Johannesburg, Madrid, Woomera. These were the deep space instrumentation facilities, still in operation today, some with larger antennas. But back then they consisted of 85-foot dishes on an equatorial mount. And whenever one of these things was aimed up in space and tracking something, you knew something really cool was happening in outer space. So, off we go. We're on the way to the moon. Takes about 4 days to get there. Go into lunar orbit, establish the initial orbit, take a couple of days to trim it down to the science orbit, and then for about 10 days, lunar orbiter photographs the moon as the moon rotates underneath it and exposes more and more of the moon to the sun. So, lunar orbiter's primary task was to shop around for Apollo landing sites. So lunar orbiter 1, 2, and 3 did that admirably. There were no major mission failures. They all made it. So lunar orbiter 4 and 5 were released to science and flew a higher orbit, a mapping orbit, to chart the entire moon. So, of course, one of the very first things lunar orbiter 1 did when it got to the moon was take a peek at the backside of the moon. Because before that, the only thing we had were these very fuzzy images from Russia's Luna 3 and one of the Zond missions. Had all the image quality of an old analog television station from 400 miles away, and all you see is snow. So, the photography by lunar orbiter was incredibly complex. Look at this diagram. We've got Earthrise, Earthset going to the right. We've got sunrise, sunset going to the left. We've got the loop of the spacecraft. We've got to be in contact with Earth to transmit the pictures. We've got to have the right illumination on the moon to take the pictures. The look angles, very complex to specifically investigate, even get stereo pairs of areas interested for the Apollo landings. And even from a high altitude orbit here from 2,800 miles, 2,800 kilometers, like with lunar orbiter 4 and 5, the look angles, very critical. The narrow angle lens, very small field of view. Even the wide angle lens, if your spacecraft is just a little bit off, you've missed the moon. So, an example, lunar orbiter 4 here. I'm trying to make my pointer work. I don't know how to make it work. Oh, the bottom one, not the top one. Okay. Here we've got A, B, C. These are, we take pictures. Snap, snap, snap. The Fuzzy area up here, we are reading out the prior frame, transmitting it back to Earth. And then a brief area where we process some frames, and then transmit more frames, and then take pictures from the far side of the moon, and then process some more, transmit them. So it's a very intricate, choreographed situation where you've got the film coming off the supply spool and looped up through all of these looping reels to take up the slack. And it's advancing through, taking pictures and processing them at the same time and trying to read them at the same time. So an incredibly complex system, but by golly, it worked. There. So finally, at the end of the mission, Lunar Orbiter is crashed. Crashed into the far side of the moon. Now, they all operated with the same radio frequency, same television, same transmission system. So you can't have two of them up there occupying the same tiny area of space. The deep space dishes are good at resolving a spacecraft, but two of them close to the moon at the same time, we're going to have signal issues. So when one mission finished its extended mission where it monitored meteorite strikes, radiation levels, and so forth, it was deliberately plowed into the backside of the moon before the next mission flew. So overall project, a success, but there were a few bumps along the way. Lunar Orbiter 1, 2, and 3, they took 212, 206, 182 frames each. The Lunar Orbiter 4 and 5 released for science mapping, and one took 263 frames due to an issue I'll talk about here in a minute, and Lunar Orbiter 5, 212 frames, Lunar Orbiter 6, ready to fly, but canceled by NASA to save a mere $13 million. Now, Lunar Orbiter 6 could have finished mapping the far side of the moon. Instead, it took until the Clementine mission in the 1990s to finally map the rest of the far side of the moon. Now, mention a couple of glitches. Lunar Orbiter 1 went into orbit around the moon and was doing quite nicely in its higher initial orbit, but notice that the high-resolution frames were a little bit smeared. The image motion compensator sensor was not working. NASA said, okay, well, we'll just leave it in that orbit. We'll be happy with the lower resolution of the higher orbit as long as the images aren't smeared. Boeing, and a fellow who's probably in charge of their safety. Today, I'm not going to say anything more. Boeing decided in their wisdom to lower the orbit anyway without authorization, and the image motion compensator still failed. They thought the lower orbit, the faster motion would jog it into activity. It did not. So all of the H frames, the high resolution frames, were irrevocably smeared on Lunar Orbiter 1. Lunar Orbiter 4, the first science mission, the aperture door, the beautiful pictures of the spacecraft we saw at first showed the guts of the inside of it, inside the frame, but the whole spacecraft is wrapped in a thermal blanket. So to see out, there's a little aperture door that pops up, lets it take pictures, and then it closes again. That aperture door stuck open on Lunar Orbiter 4. It was not going to close. Now, part of the issue is the medium resolution frames, the way the light baffling inside the camera is, if that aperture door is open continuously, enough sunlight gets through and finally bounces around those baffles and fogs the medium resolution frames. That was happening on Lunar Orbiter 4, but a fellow named Howard Pond came up with this really cool idea of using a coffee cup and sticking some pencils on it to model the attitude of the spacecraft relative to the sun. And he used that coffee cup to figure out how to point the spacecraft so the stuck aperture door wasn't light struck by the sun. And he saved the mission with that, and at a then cost of about $100,000 a frame, he done good. So, in all, 1,650 images was secured. Site 2 that was initially investigated by Lunar Orbiter 1, 2, and 3 became Tranquility Base. During the 5 missions, 18 meteor strikes were encountered, and we figured over the time span that's a relatively low flux and will be of no problem for upcoming Apollo. Radiation levels were also considered safe for the astronauts. None of them glow to this day. And the most curious thing was the phenomena of mascons was discovered on the moon by tracking lunar orbiter in orbit around the moon. We noticed that as the spacecraft was orbiting over a large Maria, its orbit would dip down. Gravity was higher. It got away from the Maria, its orbit would rise up again. So that was our first clues of the subsurface structure underneath the Maria, the wide Maria on the moon. So, what did the lunar orbiter send back? These in the 1960s were utterly mind-blowing pictures of the moon. Up to that point, the images we were taking from the Earth were, by today's standards, terrible. So lunar orbiter was just an utter revelation. Of course, first they've got to do the public relations shots. We got the Earth rising above the moon, Tsiolkovsky crater on the far side of the moon. So a very pretty picture for Life magazine. We're all familiar with the Earth rise over the moon taken by lunar orbiter. The far side, Tsiolkovsky crater, up at the top, the Mendeleev basin. These are far side images that at the time were terra incognita. We'd never seen this before. This was the first time we've seen the far side of the moon like this. Of course, the really big picture in the press, called the picture of the century, was the oblique view of Copernicus crater. They rolled Lunar Orbiter 2 on its side so it could take a shot sideways, and saw Copernicus crater from the side where you see the depth of its crater walls. A view like that had never been seen before. Another view, the Marias Hills, an area that's fascinated me for the past half century. And a little bit of a close-up of one of the Marias Hills. What shocked me is how lumpy and bumpy it was. I'd always assumed the Marias Hills were like pancake volcanoes, fairly smooth and dome-like. But instead, they're very angular and rough. A view from above, looking straight down on them. So they don't look at all like we see them in an earthly telescope. I am pushing the right button. There it goes. Now here's a real shocker that really caught us by surprise. Bear in mind, back in the 1960s, the average telescope that an amateur astronomer would have was a 4-inch reflector or a small refractor. If you had a 6 or an 8-inch telescope, you were a god. So we were getting these fuzzy views of the moon, blurry because the atmosphere is all quivery and shaky, and we could see the Alpine Valley cutting through the Alps mountains, but we had no clue that that rill runs down the middle of the Alpine Valley. When Lunar Orbiter brought that back, we were in awe. Of course, nowadays, amateur astrophotography has gotten so good that if we don't see that rill, we throw the picture away. Really. Okay, there we go. I mentioned Lunar Orbiter 4 was having issues with the film fogging due to the stuck aperture door. This is what a lot of the images ended up looking like until Mr. Pond came up with his coffee cup solution. This is what most of the Apollo landing site candidates look like. Not as smooth as they thought they would be. Just crater after crater after crater. The smaller they are, the more numerous they are. So it turned out to be a little bit of a puzzle figuring out where to put down Apollo 11, the smoothest, safest place for the first landing. More backside of the moon, we see Mare Angini up at the top. The Sea of Ingenuity, and notice the little figure 8-shaped crater down to the lower left of it, Van de Graaff on the far side of the moon. On the near side of the moon, looking square at the middle of the moon, middle of the disk of the moon, the K, the center of the K-shaped Treesnecker rills, volcanic formation. Now here's something that's of interest to the folks at Southwest Research. They're building an instrument to land near Rainer Gamma, the white albedo feature on the moon. It has no dimension to it. It's not an elevated feature, it's not a depression, it's just a different color. And it's got an elevated magnetic field around it. So Southwest Research is building an instrument to fly aboard one of the CLIPS missions to investigate what is going on here. One would think this is another view of Copernicus, but it's not. We're looking at Theophilus crater from the north. And notice Cyrillus crater on the horizon, just south of it. The Hortensius domes. There it is. See the little pancake-shaped domes there, more up here. This is more like what I expected the Marius Hills to look like, but here we're seeing the actual dome-shaped pancake formation. Kepler crater at a slant. Kepler is surrounded by a substantial ray system, but from low lunar orbit, ray systems are muted. We don't see them so much, just a few dusky streaks. Looking at the north pole of the moon from above, I like this area. Notice the cloverleaf shape of Meton crater. I call that my lunar four-leaf clover. Looking at the center of the moon again, the classic Ptolemaeus, Alphonsus, and Arzachel, and we see the evidence of volcanism, the dark ash deposits blown out of the volcanic vents around the inner rim of Alphonsus. And the crater Chicard, which we see at a very slant angle down in the lower left of the moon. Here we see an overhead view of it and the rather strange multi-hued basalts within it. Another polar view, north polar view, we're looking at the two lobes of Anaximander A and B hinging on Carpenter crater. Looks like an upside down Valentine. I love those two pair of craters, the crater Kraft up at the top and Cardanus and Rima Kraft joining them. Looks like two balloons that tied together on a string. It's just endearing. Tycho crater, as seen by Lunar Orbiter. Lunar Orbiter did not have the resolution to see that mysterious boulder sitting on top of the central peak that eventually Lunar Reconnaissance Orbiter resolved. Whoops, wrong button. And the inside of Petavius crater, Rima Petavius, extending to the upper left and the upper right. When we look at Petavius through a telescope, those rills look like the face of a clock, reading about 20 minutes to 12. Copernicus crater. This is actually a mosaic of several lunar orbiter frames that I assembled in Photoshop to show the entire crater. But Copernicus, the monarch of the moon, a classic showpiece in anybody's telescope. And the same with Gassendi crater, just north of Mare Humorum, one of my favorite four-fractured craters. The rill system looks like an oatmeal cookie right out of the oven. And another real prize. I put together this mosaic of multiple stereo mapping frames, taking my lunar orbiter of the Rima Prinz rill complex by Prinz crater. This is right next to, just east of the Aristarchus Plateau. And Prinz has been partially flooded with basalt. It's almost a ghost crater, but you can see it's distinctly slanted to the left, which is actually south. This image is turned sideways. North is to the right. And, but at the same time, we see the Rima Prinz rills emptying, flowing northward. So the high point is somewhere in between. Right in here is a high point. Everything here is sloping down to the south, here sloping down to the north. And the inside of Hevelius crater, a heavily fractured, floor fractured crater. And looking at the moon from a distance, one of the Lunar Orbiter 4 and 5 images, we see Oceanus Procellarum on the left, which we can see from the Earth, but rolling around a little bit to the far side of the moon, we see the huge circular impact basin of Mare Orientale. This is just hinted from our Earth view because it's right on the limb of the moon. It partially wraps around to the far side of the moon. And here we see the entire complex structure of these multiple impact rings. It's really made a leap in understanding of the impact nature of the lunar basins that now host the Maria. Everybody loves Messier and Messier A, the little tiny craters over on Mare Fecunditatis. They're formed by the ricochet of the same impactor. It was coming basically in the direction we're looking at, struck, made Messier A, bounced, crashed again, made Messier B, Messier A, Messier in the front, Messier A in the background. And another fun view of the backside of the moon that we've never seen before until Lunar Orbiter. We're getting down to the end of this. I'm going to get you all drunk yet. Mare Smithii up here, one of the limb-hugging seas down here. The full extent of Mare Austral, which we see part of it wrapping around to the face of the moon. And wrapping it up, another photo mosaic I made out of various lunar orbiter frames showing the Aristarchus crater on the very young, fresh crater, maybe only 200 million years old. And the highlands of the Aristarchus Plateau above it, and Schroeder's Valley, one of the largest volcanic sinuous rills on the moon that it once flowed molten lava out onto the Oceanus Procellarum. And yep, that was the last one. I always end my talks with saying there is so much to love on the moon. And as usual, I invite you to come join me on my playground.
All right, amazing talk with amazing photos. Amazing that we were able to get those photos at that time. Just really testament to the efforts of NASA. Was star tracking an advanced technology at the time of Lunar Orbiter? Or was it?
Was Star Trek?
Star tracking.
Star tracking?
Yes.
Star tracking. You mean the technology for measuring the motion of the moon underneath the spacecraft? Well, it had a star tracker to know its attitude and its position. Well, a lot of spacecraft had star trackers on them, beginning with the Mariners that went to Venus and Mars. It's a way of determining the attitude of the spacecraft so they can characterize the image that is being taken. Yeah, it was mature technology by then.
All right, next question. Have you ever considered writing a book on the Lunar Orbiter?
Well, the Lunar Orbiter itself, no. As you know, I have written a book about the moon. I think some lucky folks here in December got them as door prizes. And I will let the cat out of the bag and say that I am my own competition in the moon book business, and that I am writing another one for Firefly Books up in Canada, and it will be out later this year. So, but about the Lunar Orbiter itself, I did write a book in 1994 called The Superpower Space Race, which detailed the Russian and American exploration of the inner solar system. And I did write about Lunar Orbiter extensively in that book. Out of print, it was printed by, they're out of business. I forget their name. Anyway, that book 20 odd years ago, almost 30 years ago. but you can still get it used online, the Superpower Space Race. And I pretty much picked apart the entire robotic exploration of the moon and the inner solar system up to that time.
Thank you. All right. Just a reminder, yes, we're taking questions up there at the number. Text them in. I'll ask a question. So these images were the first real high-definition ones, and obviously they were a big part of the targeting for the Apollo mission. Beyond that, was there a lot of science done with these, or?
Yes, exactly. That was one of the beauties of Lunar Orbiter 1, 2, and 3 completing the requirements for charting potential Apollo landing sites. And Apollo and Lunar Orbiter 4 and 5 were released to science and went into a higher orbit than the lower mapping orbits, and were able to chart the entire, well, most of the lunar globe. Like I said, Lunar Orbiter 6 was canceled and could have completed it, but it wasn't until the Clementine mission flew in the 1990s that we finally plugged in the final gaps. But the basic understanding of the moon took a giant pivot with the lunar orbiters. It was more than just scouting for Apollo. It was understanding the geology of the moon, the evolution of the moon's face, the understanding of the dynamics of how the basins formed, and how everything that we see on the moon is formed by only two basic forces, either impacts or volcanic modifications. Up to that point, well, even up through the time of the Apollo landings, Apollo 17, many respected scientists still believed lunar craters were volcanic. So Lunar Orbiter went a long way to calm the waters and establish a firm science so that we understand the moon like we do today.
Was the film stepped or just continuous feed?
I then rolled off of a supply, went through the camera, went up to the processor, went to the scanner, went onto a take-up reel, and that was it. It was gone. You got your image, you got it developed, you got it scanned, you got it broadcast. There was no backing up to rescan it. So it made it to Earth or it didn't. Like I said, if there is a thunderstorm over the receiving station, there's this odd blank spot on the picture. Sir?
What lunar feature do you find yourself returning to the most when you do your observing?
Oh, I didn't hear everything you said. I'm sorry.
What lunar feature do you find yourself returning to the most when you do your observing?
It depends upon the phase of the moon. And, at the first quarter, there's lovely things along the terminator. At later phases, there's lovely things along the terminator. But I found that it doesn't matter what line of latitude the terminator is arcing across on the moon, there is always a row of really cool features. So it's like asking a parent, who's your favorite child? But there's much to love everywhere on the moon. And once you become friends with the moon and understand it, you'll find these things, and they'll become part of your friend. They'll be your friends.
Good. All right, let's thank our speaker once again.
Thank you very much.
All right, that brings us to the end of the official program. So we'll move into trivia, but first, I know some people can't stay for trivia. I hope you all can. But if you can't, please be sure to tip your wait staff very generously. They're helping us out each night. This is a large party. And I hope you come back to see us next time. But if you're staying, stay right where you are. We will get our trivia sheets out to you and writing utensils. Remember the rules. No more than 4 per group, especially because, think about it, the top prize is those lunar orbiter images. So there's only 4 that are given out. So there's more than 4, you're all going to start fighting. I just know it. So, keep it to 4. And we'll get started in about 5-ish minutes.
No, but I want one. I want one.
He's 1,000.
That's what I'm saying. Yeah, there's a bag.
No, there's not.
There it has to be. Oh, it's down there. It's good. I was like, why would somebody take out all the balls?
Or we just didn't get them.
Oh, yeah. Also, I think I need
I thought this was mine for a second. I'm just going to finish this off.
Does everybody who's playing trivia have a sheet and a writing utensil?
All right. Does everybody have a sheet that would like a sheet and a writing utensil? Speak now or forever hold your peace. All right. One last reminder. The max group size is 4. Make sure you only write the letter of the response for the multiple choice. Don't write out the full thing. It makes it harder to grade. And absolutely no cell phones allowed because we all want your brain power.
Only brain.
Only brains. 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 Question 1. Oh gosh. Forget about it.
Question 1.
Aaron's doing the odds because he's odds along that thread.
Yeah.
It helps if I turn the clicker on.
The word science comes from the Latin scientia, scientia. The root verb in blank, scientia is, God, Sam.
I gotta stand like.
All right, here we go. The word science comes from the Latin scientia. The root verb in scientia is scire, meaning what? A, to be, B, to think, C, to study, D, to know, or E, the hot dogs are burning. What?
You know those Romans and their hot dogs, or Greek? Is it Greek? No, yeah,
Roman,
Romans.
yeah.
Romans and their hot dogs. Yeah.
They invented the hot dogs. Did you know? Does anybody know any kind of Latin? To know like what the SC sound makes in Latin?
It's gotta be.
It's one of 3 pronunciations. Ska, skira, or scientia, or skira. Then us Americans bastardized it and just made it science.
It could be C. Sira.
It's either Sira or Skira.
I don't know. The problem is all the Romance languages are all different, so there's no help. All right, has everybody got on this question? All right, question 2. Saturn's moons. Which of Saturn's moons was the first to be discovered? A, Rhea, B, Titan, C, Hyperion, or D, Enceladus? All right, there are 2 bonuses with this one, so just write it next to your letter on the line of the question. Bonus 1, who made the discovery? And bonus 2, when was it discovered? And I will say that this question, hopefully tonight's talk helps. Hopefully. But also, for the bonus 1, once again, hopefully tonight's talk helps. Just going to leave it there. Bonus 2, you're on your own. That was... Can hear the train going. I caught 2 today. I caught 1 going this way and 1 going that way.
On the way over.
Yeah.
Wow.
I went over to the tunnel.
That's
I wasn't
incredibly
going to
unlucky.
wait. I wasn't going to wait. The train ain't stopping me. All right, are we all good on this one? I know we have bonuses, so I don't want to rush you through this. All right. Aaron?
Everybody good? All right, question 3. Using X-rays to get real-time images of the body during surgery is known as what? Is it A, radiometry, B, positron emission technology or tomography, C, fluoroscopy, D, magnetic resonance imaging, or E, seriously, the hot dogs are burning. Please get them off the oven. We need them for dinner. Thank you.
Man, our trivia man phoned it in on this one.
If I see E on any of these trivia sheets, zeros all around.
I think he was hungry when he made this.
Were they serving hot dogs in the cafeteria that day?
All right, good. Question 4. An expected question. The tadpole-like lunar structure, sometimes called the Sweary spot, is known by what official name? Oh, goodness. A, the Straight Wall. B, the Apennine Trail. Oh, I'm pushing a button. C, Reiner Gamma. D, Hadley Rill. Or E, oh, God. Burned hot dogs. Once again, more bonuses. Write them next to the response. Most creative nickname gets 2 extra points. So this is a very subjective question. We're really leaning into it today.
Michael and I are grading. I don't know what that provides, but the great what? The great Bella structure. Ballpark for yeah, probably.
No, they got to be Nathan's. It's Nathan's or nothing.
Sam, you were seriously hungry during this. I'm sensing a theme. Everybody good on this one? Going once, going twice. Question 5, a trained eye. Name that thing. Is it A, Mercury, B, the far side of the moon, or is it C, Ganymede? I like this question. This is a pretty good one.
Name that Pokemon.
Man, I haven't seen that in so long.
It's Pikachu.
God.
No, don't give him ideas.
This is the perfect opportunity
Don't
for hot
give him
talk.
ideas. Honestly, all right, raise your hand if you think question 6 is going to have a hot dog response. I don't know. I think it will. All right, let's see. Question 6. Oh, wow, there's no hot dog. Okay. Lone Star Astronomy. Oh, right here in Texas. Built in 1996, the Hobby Eberly Telescope is Texas's largest telescope. Located in which Rocky Mountain range? Is it A, the Chisos Mountains?
Chisos.
I'm sorry, Chisos Mountains. I'm sorry, I'm thinking of chai latte. I am, yeah. I should have said it in Spanish. God damn it. B, Franklin Mountains. C, Sierra Diablo. D, Palo Pinto Mountains. Or E, Davis Mountains. Which one will you find the Hobby Eberly Telescope?
Honestly, Hobberly.
Hobberly Telescope. There we go.
It's a quick nickname.
That's my creative nickname tonight.
Has anybody been to the HET? Wait, Caleb, you have? Caleb. Caleb. I'm going to have an intervention. I'm going to have an intervention. If you haven't been, I highly recommend. It's the HET, like the big one. You can drive up to the dome, you can drive up to the mountain, and there's a big window that you can see the entire telescope. I lost my marbles when I drove up there, and it's like I literally ran up to the window, like as a child. Like
Is that the window?
Yeah, right inside that door, there's like a big window where you can see the actual like mirror. It's a big segmented, hexagonal segmented, like colossal mirror. Yeah, if you haven't been, highly recommend.
All right, we ready for the bonus?
All right, bonus round. A temporary reprieve. Discovered in 1995, 51 Pegasi b is the first exoplanet discovered to orbit a sun-like star. However, its unique properties are unlike anything present in our solar system, resulting in a new class of exoplanets known by what name? bonus to the bonus. Correct answers are awarded 1 point, but the best wrong answer is given 3 points. So there's lots of extra points up for grabs here.
This incentivizes it to get it wrong.
Yeah, it does.
Or how about this? You can get 4 points if you put the right answer and the wrong. Let's do that.
No?
No?
Okay. One answer. You get one answer. Yeah, you bet. Do you know it? Or do you think you have the best wrong answer? Again, Michael and I are grading, so.
"51 Pegasi b is the same planet that was in the Fellowship that Xinting won. So we've come full circle.
This wasn't the first exoplanet discovered, was it? The first one was around a pulsar, right? Yeah. Sun-like. Yeah, gotcha. Yeah, I don't know the answer to this one. I don't know the class of exoplanets.
When you are done with your response, first of all, does anyone need us to revisit a question at all? Yes or no? No, I'm seeing no. So when you're done, come up with your sheet. If you used one of our pens, please give it back to us so we can keep using them in the future. Thank you.
Everyone's good on questions?
All right, so as usual, we will grade the responses. So this is a mini break, and then we'll reveal the answers and then dish out the prizes. So give us a moment.
All right, we are tallied and totaled. We're going to go over the answers. The first question was about something I don't remember.
Yeah, I don't either. Oh, the science.
Ah, the fucking hot dogs. The word science comes from to know, not hot dogs. Please do not walk out if you're thinking it's about hot dogs. It's not. It is green, but Latin is beyond green.
Our trivia person was extremely hungry.
He was missing baseball.
Nobody put E.
Yeah, no, thank you. No one put E. Seriously, thank you. That would have been.
All right, so the next question was on Saturn's first discovered moon. The answer, oh please, I hope you put this down, was B, Titan. We talked about, or Xinting talked about how Titan is bigger than our own moon. So that means it's quite large and
Quite
would
large.
be easier to discover from afar. And by afar, I mean Earth. And then the discoverer was Christian Huygens. And once again, so the Cassini mission was not just the Cassini mission. It held a probe called the Huygens probe, and this is why. And the probe happened to land on Titan. So it all comes together. So 1655
Yeah.
is the mid 1600s.
We are going with the closest, yeah. Question
Yes.
3 was
Question
something
3.
I don't remember. Oh, yes, using X-rays to get real-time images during surgery. Fluoroscopy. I did not know that. Fluoroscopy.
No,
So-
not E.
God, yeah, no, God damn it, Sam. Not E. So, like, they inject something, and then it's fluorescent, I guess? Yes. Huh?
All right, question 4, which had the fun bonus of make a fun creative name.
We got some creative names.
There were some good ones. C, Reiner Gamma. It came up during Robert's talk, so this is a memory recall question. Yes, Swiri is going, what is it called? Lunar Vertex?
The
Somebody correct me. I don't know if you know, Robert, the name of it. I think it's called Lunar it's either Vertex or Vortex, because both work.
Wait, for what?
For the Swiri mission.
Oh,
It's
Yeah,
one of those names, but yes, we're excited about it. Reiner Gamma is a very unique magnetic phenomenon, and the reason people think that the color is lighter is because the magnetic field is blocking the solar wind from impacting it as hard as the rest of the surface, so it's not getting weathered. So the best way to study it, of course, is to go there and analyze this phenomena. So get excited.
do we want to say what the most creative name was without giving the team name away?
Well,
It was the...
oh. Do we want to say that?
I'll say it. I'm not afraid.
I mean, because of the look of some of the features on the moon, this name was extremely creative, and you know what? It's scientific. It is scientific.
It
It
is.
was Squiggle McSquiggle sperm. It's very scientific, folks. Question 5.
It's Mercury. That's why I really like this question, because they all, well, except for Ganymede. If you've seen Ganymede before, it's kind of dark, I guess. Yeah, but this question was cool. It was a good question, Sam.
There is a lot of overlap between lunar science and Mercury science, interestingly enough. A lot of people that do one will either work on the other or have tangential relations to the other. They're a lot more similar than you might think. Mercury, however, does have its own intrinsic magnetic field that the moon doesn't.
That I found, as Jared told me, is non-central.
Yes,
Yeah,
allegedly, yes.
Oh, okay, allegedly.
All right.
Who knows?
Okay,
got
question 6 was, the Hobby-Eberly telescope. The Hobberley telescope.
The Hobberley.
It's in the D.E. Davis Mountains.
E. Davis Mountains.
Hobby
Hobby-Eberly.
Eberly.
But seriously, highly recommend if you have not gone. Not only is it a beautiful drive through the Davis Mountains, just that whole area is so cool to go to. You learn a whole lot when you go. Yeah, it's about, I think it's like a 7-hour drive. It's not, for Texas, not too far. It's down the road. Those are completely different opposite directions. I'll tell you what.
All right.
I don't know much, but I know that.
Bonus.
The bonus with bonus and bonus.
The planet, the first exoplanet
51
discovered.
Pegasi B.
What was the first exoplanet discovered?
What's the classification?
It's not just any Jupiter. It's a
Yeah. It's hot Jupiter.
really hot. Now, the reason they're called hot Jupiters is because they are Jupiter-sized. They are Jupiter compositionally. They're like gaseous, but they're really close to the star. Hence the hot part. And it is a conundrum because, you might think it vaporizes, but they stay together. And in some cases, here we're going to do some fun tying together here. Some hot Jupiters have been found to be vaporizing a trail around the star, and this phenomena has been observed by the Hobby-Eberly telescope. I can't do this.
You got it.
The Hobby-Eberly telescope. So, really interesting stuff. So that's why hot Jupiters are notable in our field. The best wrong answer was, I didn't really find a good one on this one.
So the two best ones, the bonus to the bonus, the two best responses were spicy planets.
Oh, yeah.
That was good.
And
honestly, my favorite, sauna Saturns.
Yep.
I love the
like
alliteration.
that one.
That was good.
That one wins it for me. Sauna Saturn. Good job. All right. We've come to the part of the program where we dish out our prizes, and thank you for winning. In third place, for being the closest on the year, Epwitty. Congratulations. The third place prize tonight are 3 Sky Almanacs and 2 totality books written by Jeffrey Bennett. In second place, for having the most creative Reiner Gamma nickname, is the Stream Team. They will win also 3 of the almanacs and a tumbler for the eclipse that happened in October. So close enough. Still an eclipse. And the number 1 prize, winning Robert Reeves's extra 4 of 3,000 lunar orbiter prints. Drum roll, please. %, team, _name, %. Woo! Congratulations. You won some amazing lunar orbiter prints. We hope you get them framed and hang them up somewhere fun. Give them away. Oh, yeah, the honorable mention.
The Star Master.
The Star Master. Who is the Star Master? Great job, Son of Saturn. And who was the Spicy Planets was Lunatics. Who's Lunatics? Great job, great job. But a really great job to all of you. Thank you for coming. Thank you for coming. Our next AOT, April 3rd, a big reminder. This AOT is the Wednesday before the solar eclipse. We're going all in. We're going to have the chair of our physics and astronomy department, Dr. Angela Speck, speaking about the eclipse. We will also have another fellow UTSA graduate student, Cody Cly, speaking as well. So it's going to be a great event. Tell everyone, tell all your friends, bring them on down. We're going to have a great time. We'll see you then. Thank you for coming. And thank you, of course, to the Blue Star Brewery and the Southwest Research Institute for their continued support, and UTSA.